Hello everyone, my name is Andrew Matson. I'm taking Math A252 or Calculus 2 with Dr. Graham, and for my final project I'm going to be talking about polar coordinates. Just so you know, I do have some construction going on, so if you hear some sound in the background, that's what it is. So first off, what are polar coordinates? Polar coordinates are just another coordinate system, but instead of using an x and a y like the Cartesian coordinate system, they use a radius and an angle. So what does that mean? The Cartesian coordinate system uses an x and a y, meaning it first tells you how many to move over, and then it tells you how many to move up or down. The polar coordinate system uses a radius and an angle instead of an x and a y, the radius being the length of the line, and the angle being the angle of the line. The starting point of a polar coordinate is called the pole, and that's something we have to keep track of, usually using Cartesian coordinates. So where did polar coordinates originate? Hipparchus, who was a Greek astronomer, is thought to be the first person to use polar coordinates, at least in recorded history, as he used them to record the positions of stars from 190 to 120 BC, and later on in 800 AD, some astronomers were seen using polar coordinates, or systems very similar to polar coordinates, to calculate distances from important places. So coming into the modern day of math and physics, Isaac Newton is thought to be one of the first people to truly conceptualize and write down the system of polar coordinates. And in 1671, he proposed 10 different varieties of coordinate systems, and polar coordinates were one of those systems. The problem with that, though, is that Newton focused more on tangent lines and how you could determine them with these different systems. But a man by the name of Jacob Bernoulli, he looked a little bit further into the system and wrote expressions that pertain specifically to polar coordinates. And his work was published in the early 1700s before Newton's work was published. So for a long time he was thought to be the one to do it first. So what are some of the applications of polar coordinates now that we know what they are and where they came from? One of the biggest uses for polar coordinates is navigation. And this sort of makes sense because boats and aircrafts, they need to know the distances to objects, and then relative to a compass, they need to know what direction to head. And polar coordinates do exactly that. They tell you how far you are using the radius, and the angle that you have to head relative to the North Pole in order to get to that object. The other application for polar coordinates is one of my favorites because I am a computer science major, and that is computer science. A lot of modern computer games utilize polar coordinates when figuring out where objects are relative to other objects, or where to place them and render them on the player's screen. Polar coordinates just seem to do this best over other systems like the Cartesian coordinate system. So then, knowing the applications, what are some application problems? Here's an example problem pertaining to computer science. A video game must render a box on a 2D plane relative to a player. If the player is at 0, 0, the Cartesian point 0, 0, and the box is one square unit with its bottom left corner at 3, 4, what are the polar coordinates to each corner of the box that the player can see? So here I've drawn it out what the question is asking. So here's the player in the bottom left. Here's the box it was asking about. And we can see here that the bottom left corner is at the point 3, 4. And we're asked to find the polar coordinates for each of these points on the square relative to the player. Starting with point B, since we know that the corner is at 3, 4, this is easy. A 3, 4, 5 triangle means this is going to be 5. So that's our radius. And then to find the angle, we take the tangent of the opposite over the adjacent, and we can get that theta equals 53.1-ish degrees. So here's our first one for point B. Point A is a little bit different because we are now up one more. So it's now 3, 5. And this isn't a 3, 4, 5 triangle. This is confusing. The legs have to be 3 and 4. So as it turns out, the hypotenuse is actually going to be the square root of 34. Which can't be simplified any more than that because 2 times 17 is 34, and 17 is a prime number. To find the angle theta, which I did not label, but this angle here, we take the tangent inverse of the opposite 5 over the adjacent 3, and we get 59.0 degrees. And there's our polar coordinate for A. And then finally for C, we now have moved over 1. So our triangle looks like this with a 4-4 triangle. And we know that if we have a triangle with the legs being the same, that it'll be x, x, and x root 2, so we can get 4 root 2 for our hypotenuse, or we can use the Pythagorean theorem. And we know that this will be a 45, 45, 90 triangle, so we can say theta is 45. And I also forgot to label it, but this angle is 45, and then we are left with the radius, 4 root 2, and 45 degrees for our polar coordinate. So the second application problem is the following. A player in a 2D game rotates, changing the angle they face by delta theta. How will the polar coordinate of a point at a fixed distance from the player change if it starts epsilon degrees from the player? So this is a little bit interesting to think about, but here's our player, as I've drawn out. This is the direction they're facing, and we are changing that direction by delta theta. And the fixed point, meaning the radius is fixed, is at the angle epsilon, is what it starts at. So if delta theta, which is our change in theta, happens to be equal to 30 degrees, our epsilon, as we can see here, is going to be delta theta plus the existing epsilon, and then the same goes for if it's negative, it'll just be adding that delta theta onto the value, so plus a negative is minus 40. And so we can sort of see here, we can also see with the drawing that therefore the polar coordinate is going to be the existing fixed radius, and the degrees are epsilon, the existing or the starting angle, plus the change in the player's angle. The point never changes location, but the angle will because the player is rotating, and since it's relative to the player, the point changes. So the third application problem is, a player in a 2D grid moves up 1 and over 2. How does the polar coordinate relative to the player's north axis of a fixed point change if it starts at 5 and 150 degrees? So here I've drawn this out. It doesn't tell us where on the coordinate system everything is located, but we know that if the fixed point is at 5 and 150 degrees, that it's going to be down 5 from the player and 150 degrees down. So I have that drawn here at 150 degrees, 5 down is our point, and I just place that at 0, 0. So that tells us that our player is somewhere in the first quadrant, we just don't know where to start with. So what I did first is using these equations that were actually in my intro here, x equals r cosine theta and y equals r sine theta, I found that y is going to be equal to 5 root 3 over 2, and x is equal to 5 over 2, just based on my drawing here with my triangle. So we know we start at that point, 60 degrees, x is 5 over 2, y is 5 root 3 over 2, radius is still 5, and we're going to go to 9 over 2, or 5 over 2 plus 2, to 5 root 3 over 2 plus 1, because we're going up 1 and over 2. So here I've drawn our new triangle. This is our first triangle. I drew our second triangle. Now we know the length of our legs, but we don't know our radius and our angle. So solving for our radius, we can use the Pythagorean theorem, and we get that our radius equals approximately 6.98. Theta, then we can solve for using the tangent inverse of our opposite leg over our adjacent leg, and that looks a little bit ugly here, but then we can get theta equal to 49.82 degrees, and our final answer is going to be a radius of 6.98 and an angle of 139.82, because we're actually adding that initial 90 degrees back onto our angle. So just as another example, I programmed up something simple using polar coordinates that circles a point around a center point. And the basic principle behind it is all in this getXy function here. It returns the x value, which is equal to the radius times the cosine of the radian angle plus the existing center. And so that is our initial program, which is x equals r cosine theta. with theta equal being this and our radius as our radius. And then we're adding our center on each of these. And here we have our change in our angle at each point, which I've just set to 45 degrees to start with, but we'll change it as it goes and see what our program looks like. So here's the program with our angle set to 45 degrees still. As I increment forward, we can see that it moves 45 degrees down, 45 degrees more, so 90 degrees, then 135, then 180, and this keeps going all the way around the circle. So what happens now if we change our angle to 30 degrees? Well, it's what you'd expect to happen. Now, the angle changes forward by 30 degrees instead of by 45, and we can see that now we are at 120, 150, 180, 210, and that goes all the way around the circle. So just to experiment, let's set our angle equal to something different, like 54 degrees, just as a random degree number. Let's see what our angle changes to look like as we go through here. So, as we can see, it's now no longer lining up with any of the axes very well. It will line up with the axes just because of how the program works. It has to fit in one of these points, so it approximates and tries to figure out which point it should sit in. So ending off my presentation, here are my sources. I hope you found something informative within my presentation, and I wish you a great summer.